Now let's go to MATLAB. This view is clear. Close all. And the first thing we're going to do is create the data variable, and we're going to load in our text file. So our text file is p_Reynolds, etc., etc., etc. Now we're going to say our x is going to be the first row, the first column of this matrix. And similarly, the y and p here. Pressure 2. This is 3 all the way to the end. So pressure's 3 all the way to the end. So next, we're going to recreate what we had in COMTOL. 3, E, 1 is equal to 5 times D, H equal to 17 times D. Now Cx is equal to 5 times D plus L. To get L, let's find the length ratio. We said it was going to be 2. And this makes the length equal to length ratio times the diameter. Let's do our second cylinder. Already did the length ratio, so now let's do the diameter ratio. So the diameter ratio is 1. It makes the lowercase d equal to diameter ratio times diameter, the larger diameter. Now let's also define alpha to be 30 degrees. And we will also define the average diameter as this average right here. Now we can move to our flow. We're going to say that Reynolds equal to 300. The density 1,000. Viscosity of 1e to the minus 3. And our velocity is going to be the Reynolds number times the viscosity divided by the density times the average diameter. Now we're moving to the time step. Saying the Strouhal gas is equal to 0.5. The F gas is equal to the Strouhal gas times, let me pause it. Yeah. So let's go to this, and we'll say that it's going to be U over the average 1 T gas would be 1 over F gas. And 10 delta T is equal to T gas over N. Now our NN is equal to 100. And our final time is going to be delta T N. And our start time is going to be time minus T equal to W over U plus 2.5. Okay. And now our output time is going to be the T1, again, 0, 0.2, time start minus 0.2. Now our T2 is equal to time start delta T time start plus time. Our whole output time will be T1 comma T2. Now let's also put the grid. Grid X equal to 50. And our grid Y equal to 34. Now let's go ahead and we're going to define one more variable up here. It's going to be Fs, which is equal to 1 over delta T. Okay. Now let's continue on here. So let's say that capital X is going to be a reshape of lowercase x. Now the size is going to be grid X, grid Y. We'll do the transpose of that. Let's copy this. And go ahead and do that for the Y variable. Now let's create this, we're gonna get the amplitudes and we're gonna input the pressure and then get the largest pressure oscillation from that. So let's see. Let's create that function. So we're going to say for I is equal to 1 to the size of P in the first direction. So it's going to run through each probe location. And we're going to say our temporary is equal to T in the I row in all the columns. Okay. Now we'll say temp equal to temp minus mean the temp. We're subtracting the mean. We'll say L is equal to the length of temp. Now we're going to do N is equal to 2 to the next power. It's power of 2 L. Now we're going to say our amplitude is equal to FFT temp N. Okay. Now we're going to break it down. We're going to say A is equal to absolute value a 1 to n over 2 divided by n over 2. Okay. Let's also define our frequency. F is going to be equal to Fs times 0 to n over 2 minus 1 over n. Now we're going to have to input that for a function. Put it here as well. Let's go ahead and say what we're doing next here. So what are we doing next? We're doing peak, I, and log I is equal to maximum of A. Okay. Actually, let's go ahead and save our amplitudes and our frequencies. Perfect. Oh, actually, this is going to be rows and columns. This is a vector. Rows and columns. Now we're going to say our maximum peak is going to be equal to max of pk. Now our frequency of vortex shedding is going to be F. All right, let's get our FFF. It's equal to FF lock, comma. Okay, and our AA, lock. From there, we have to identify our frequency of vortex shedding. FPS is equal to FFF FFF is going to be a vector. So we want to get the location for the lock. Let's put that here. PP FFF AA and F. Yes. Run it, see what happens. What we're going to do next, so that pressure is equal to reshape. We're going to plot the contour plots, contour f of x comma y over d, I, d, and then pressure. Okay. But first, let's go ahead and get the max. After that, do a figure where we lay out. Go ahead and pause this. I'm sorry. We want to put PK right here. PK. And I don't think we need PP in this case. Any there. Now we can get rid of that. And now it should work. So let's see. Got a PK. Under. Okay, so you actually want to include LOCC as well. So let's bring it back up here. Okay, this is the pressure intensity. So let's add a title right here. Title. Actually, we'll say intensity of the pressure oscillations. Okay. We'll do a save as PCF. Say Reynolds 300, and we'll go ahead and say pressure density, and this is 2 cylinder. We'll save it as an SVG. Now for this other plot, we're going to try to get, one other thing I forgot to do was remove the transient data. So let's try to do that right here. Because we want the steady state solution. I'm going to say P can be 1 in all the rows of the 1, 2 length T1 are equal to nothing. You might see a different plot here. But now we can go to, we're going to plot our time series. So we're going to say 2, comma, E from block all the rows. Okay. Do next tile. F, AAA, and we're also going to multiply by the diameter average, divide by this. So that'll be the Struhl. We're going to add markers, okay, to show how many samples we have. Now let's go ahead and display Struhl is equal to FES times D average over E. Okay, so let's review. We saw where the pressure intensity is, and then we got our probe location from the highest pressure intensity of oscillations. And then we plotted our time series from there and our frequency domain. And then we took the non-dimensional vorticity as the Struhl number.